In our previous two videos, we talked about how ease solves equations. The video entitled Guess Values and Stop Criteria discussed the importance of providing a good set of guess values to help ensure that ease converges. In the video entitled Using Ease Effectively, we discussed how to use ease in a sequential manner in order to facilitate debugging a large program and also to ensure that ease has a good set of guess values. This video is going to talk about how ease blocks large equation sets into smaller subsets that can be solved independently. This discussion allows the user to understand the residuals window in ease, which can be helpful for identifying and isolating convergence problems in a large set of equations. Even though you may have what looks like a large set of simultaneous equations, it is often possible to solve these equations in smaller groups or blocks rather than solving all of the equations simultaneously. Solving equations in blocks is more reliable because it reduces the number of variables that must be determined at any one time. Blocking also reduces the required computational time. Ease automatically organizes the equations that you enter in the equations window into blocks before it attempts to solve these equations. This reorganization occurs regardless of the order that the user uses when he enters the equations in the equations window. To illustrate this method, let's consider the set of equations that's shown here. These are 6 nonlinear equations in the 6 unknowns that are highlighted by these red boxes. These are the variables a, b, x, y, c, and d. So here these equations have been entered into the equations window in ease, and by selecting solve, I can obtain the solution that's shown here. Ease automatically reorganizes these equations so that they can be solved most efficiently. So first, ease is going to recognize constants, that is, variables that are directly assigned a value. Here x equal 1 falls into that category. Next, ease recognizes single equations and single unknowns. Because the value of x is now known, the equation y equals the square root of x plus 2 is a single equation in the unknown variable y. The constants in single equations are grouped together in what is referred to as block 0, and they are all solved before moving on. Next, ease looks for subsets of equations that can be solved together. So here, given the values of x and y from block 0, these first two equations are two equations in the unknowns a and b, and they can be solved together before proceeding any further. These two equations are grouped together and placed in block 1, and then solved using Newton's technique. Finally, the last two equations are two equations in the unknowns c and d. They're placed in the next block, block 2, and also solved together. The result at this point is that all of the equations have been solved. We have a complete solution, but in no case did we ever have to solve more than two equations and two unknowns simultaneously. Blocking equations is indispensable as it reduces the required number of iterations that's needed to solve the problem and improves the likelihood of finding a solution. It's much easier to solve several small sets of equations versus one very large set. The result of the blocking and reordering process in ease is most evident in the residuals window. Knowing the organization that ease is using to solve your sets of equations can be very helpful in order to understand the nature of the problem that you're trying to solve. And it's also very often helpful for debugging purposes. This information is all provided to you in the residuals window. So here let's go back to the ease code that we started with, which solved that set of 6 equations and 6 unknowns. To view the residuals window, select Residuals from the Windows menu. The first column in the residuals window shows the block number. So here note that the blocking process has resulted in the same result that we identified manually for this system of equations. Equations that have a single unknown or can be solved one at a time have been assigned to block 0. Also notice that the order that the equations appear in block 0 are the order that ease is attempting to solve them. So for example here, ease has chosen to solve the equation x equal 1 first, even though it was the second equation entered in the equations window. With x and y known from block 0, the two equations in block 1 can be solved simultaneously for a and b. Notice that the variables a and b are shown in bold in the rows for block 1 in the residuals window because these are the unknown variables in this block. Finally, block 2 is solved for the unknown variables c and d, and these two variables are shown in bold in the rows here for block 2. The variables not shown in bold in block 2 have values that have already been determined in the lower blocks, in this case block 0 or block 1. The residuals window also displays the relative and absolute residuals for every equation in the main program. The absolute residual of an equation is the difference between the values on the left and the right sides of the equation. The relative residual is just the absolute residual normalized by the value of the magnitude of the left side of the equation. ease monitors the values of the relative residuals during the iterative calculations to determine when the equations have been solved based on the stopping criteria that the user has set in the options menu. The units column in the residuals window indicates the status of the unit checking. So OK here is going to appear if ease didn't find any unit checking problems. In this example, there are no unit conversion problems because we didn't enter units for any of the variables. But if we, for example, set the units of the variable A to feet and then we resolve the problem and look at the residuals window, you will notice that there's now a question mark in the units column for these equations. If you click the right mouse button on the question mark, you will get this pop-up menu to appear. And the pop-up menu provides a few options for addressing the unit problem. One of the options is just to disable the unit checking for the selected equation. If the unit checking for an equation is disabled, then the units column will show an X, as shown here. The number of times that the equation needed to be evaluated in the process of obtaining a solution is shown in the calls column of the residuals window. Note that this number includes the calls that are needed to evaluate all the numerical derivatives required by Newton's method. A very large number of calls for an equation may indicate that the guess values for the variables involved in that equation are not very good. The residuals window allows you to see behind the scenes and understand how ease is organizing your equations in order to find a solution. In the event that your problem is not converging, the residuals window allows you to isolate the problematic subset of equations or block, and therefore may guide your debugging process.